For this lab, I analyzed the motion of a spring with a mass hanging on the end moving with 2D motion. Using the program tracker, I plotted the motion of the system. Using data found from the 1D spring motion video, as well as some of the data from tracker, we were able to create a computational model of the motion of the spring. From the lecture video which analyzed the 1D motion of the spring, we found that the mass of the object is 0.402 kilograms, the spring constant is 6.83 newtons per meter, and the relaxed spring length is 0.123 meters. I then took this data and plugged it into VPython. The initial position, negative 0.114, negative 0.638, and the initial velocity, 000, is imported from the tracker video. I then took this data and plugged it into the VPython. From there, we can start plugging in equations to create the model. Starting from Newton's second law, F net equals ma, we find that there are only two forces acting on the mass, gravity and the spring force. That means that F net equals the force of gravity plus the spring force. To find the velocity, we use the equation V final equals V initial plus F net divided by mass times the change in time. For position, the equation is the final position equals the initial position plus V final times the change in time. I plugged that data into VPython. We still need the force of gravity and the spring force to compute F net. First, we find gravity using the equation the force of gravity equals the mass of the object times g, which is negative 9.8. Here it is in VPython. Then we find the spring force using the equation spring force equals negative 1 times the spring constant times s times L hat. S is the compression of the spring, which is the magnitude of the length of the spring minus the relaxed length of the spring. The length of the spring is the position of the object minus the attachment point of the spring, 0, 0, 0. L hat is just the unit vector of the length of the spring, which is L divided by the magnitude of L. Here are the equations in the code. From here, we can run the code, and it will show the motion of the spring. The graph here shows the computational model, the blue line, and the tracker data, the red line. We can see that the two lines are not perfectly the same, but that is mainly due to the variance in the tracker points and drag, which slows the mass down a little bit. Otherwise, the VPython model does a good job at modeling the motion. Using the energy principle and some data found from tracker and the force data, we can show the changes in kinetic energy as well as spring and gravitational potential energy over time. Since our system is the spring, the mass, and the earth, we assume that no work is being done on the system, and the change in energy is 0. Here's that information plugged into the code. We will see when the various forms of energy are graphed, the sum of the changes in energy is 0. The kinetic energy equation is 1/2 times mass times the velocity squared. The change in kinetic energy is the final kinetic energy minus the initial kinetic energy. Here it is plugged into the code. The gravitational potential energy is mass times gravity, which in this case is 9.8, times height. The change in gravitational potential energy is again just final minus initial. Here it is in the code. Finally, we need the spring potential energy, which is 1/2 times the spring constant times s squared. The change in spring potential energy is again just final minus initial. And here it is in the code. Now we can run the code again, but this time the graph will show the 4 types of energy. The change in kinetic is blue, the change in gravitational potential is red, the change in spring potential is green, and the change in total energy is yellow. Here we can see that the 3 changes in energy create sinusoidal graphs, but the total energy remains at 0. To answer the first "what does it mean" question, this means the motion of the spring and the computational model satisfies the energy principle. For the second "what does it mean" question, we need to find the period of oscillation for both the x and y data. For x, we start at t equals 0 and choose the next 3 points where the mass starts to change direction after completing a full period. For y, we start at 0.76 seconds and again choose the next 3 points where the mass starts to change direction after completing a full period. We calculate the average of both of these periods and find that for x, the average period is 1.65 seconds, and for y, the average period is 1.52 seconds. The period of oscillation for x depends on how far in the x direction it starts out, while the period of oscillation for y will always be about the same, whether it is experiencing 1D or 2D motion.